Today's video is on quantum gravity. Hello, my name is Bob D. Hilster, and I am your particle model guru. Quantum gravity is one of the 5 problems that I listed in a previous video. The first of the 2 videos that I've made was a summary of the 5 problems, which you can get from this link. And the last one I did was problem number 5. I started with number 5, dark matter and dark energy, which you can find at this link. And you may want to at least look at the first one before proceeding. In any case, today we're moving on with the quantum gravity problem number 1. This is the 5 great problems that I found on the internet, found it at this link from ThoughtCo. They listed it in March of 2018. And they listed 5 of them. And as I said, I've already talked about number 5, the cosmological problems that are being referred to are dark matter and dark energy. Problem number 1 is titled quantum gravity, and the challenge here is to combine general relativity and quantum theory into a single theory that can claim to be a complete theory of nature. Turns out that this is from Lee Smolin's book, The Trouble with Physics, and happen to actually have a copy of this, if I can put it there properly. There you go, Lee Smolin, The Trouble with Physics. And as usual, I probably stole this book from my son David. Eventually, he'll get it back. Doesn't matter. He kind of grumbles at me a little bit about that, but I still do it. Okay, and so what Lee Smolin is trying to say is combine these 2 in some way, but he's really leaning in one direction. He wants to make general relativity, he wants to make the gravity fit the quantum theory. And quantum gravity, in general, is a field of theoretical physics that seeks to describe gravity according to the principles of quantum mechanics, that is, making gravity fit into quantum theory. In chapter 1 of Smolin's book, it is actually titled The 5 Great Problems of Theoretical Physics, and on page 5, he states there are 2 realms in physics. In the atomic realm, where quantum physics reigns, we can usually ignore gravity. So you look at the atomic level and forget gravity. In the realm of gravitation and cosmology, we often ignore quantum phenomena. So the 2 aren't really working well together at all, and they're having trouble putting them together. Well, Lee Smolin is really proposing a one-sided solution that I've sort of hinting at. By labeling problem number 1, quantum gravity, the solution becomes one-sided. Gravity must fit with quantum mechanics, quantum theory, whichever name you want to use. The question is the reverse not an option? Is it impossible to talk about gravity at the microscopic level? Well, guess what? One of the things I recently remembered is Coulomb's force law, which was developed in 1785, is that the electric force is equal to Coulomb's constant times the charge, well, that's supposed to say Q1 and Q2, divided by the inverse square law. And it was quite remarkable at the time because it looks like Newton's law of gravity. I remember this in college. We thought it was interesting that Newton's equation and Coulomb's equation looked alike. Did we ever ask the question, are there two gravities? Well, in a sense, they discarded Coulomb. Problem 3, I'm going to review a little bit of that here as well, suggests that physics needs to be unify the forces and particles of the standard model. Since I brought up electric force, that's what I'm talking about, the forces. And the standard model talks about 4 forces. Gravity is in one realm, as Smolin indicates. Electromagnetic, nuclear strong, and nuclear weak are in the second realm. Well, and I just mentioned electric force, and it's not there. Did they throw it away? Does it not matter? Okay, the standard model and the graviton. And if you look at this standard model with its 17 particles, there's 16 here, 4 by 4 plus the Higgs. And they, in this particular graph, they stuck on the end because they know they have to have gravity, and they call it the graviton. Well, the graviton is a name for a gravity particle that is part of the Lesage theory, which was invented about 100 years after Newton. But if you go and look up in the full wiki, you look up the graviton and Lesage, you'll read this statement. By the beginning of the 20th century, Lesage's theory of gravity was generally considered to be conclusively discredited. Mainstream doesn't even consider it, but they use the name that was developed during the when Lesage's theory was being seriously considered. And some do today, including me. So mainstream science doesn't use this theory. They'd rather develop a theory of quantum gravity than use Lesage's theory. Well, some of the problems that mainstream has is making wrong decisions, and one of them is the forgetting the electric field. And it's not wrong to study a theory and decide that you think it's not worth pursuing. But it is bad when you totally exclude a theory, like Lesage's theory, because everyone says it's wrong. So if a mainstream scientist suggests that they're going to use it, everybody kind of looks a little bit funny at them, wondering, oh, what in the world do you think you're doing? You could also say that an object can never go faster than the speed of light because someone said so and everyone agrees. So you don't want to talk about anything going faster than the speed of light. The problem with these bad decisions, and ones like it, is that when a scientist does this, he has closed the doors to some possible solutions. And if you're a scientist, you can't do that. You really can't do that. You've got to have an open mind to a lot of ideas. And actually, if you listen to my son's David videos, you realize that he's always looking at other theories, even though he may not be his most favorite theory. But you can find out, you can get good ideas from other theories. Got to keep an open mind. You just can't say, sorry, it's wrong, we're not using it. Well, it turns out in both of these bad ideas, the particle model uses both. Again, I said this, if you're a mainstream scientist, you better not talk about Lesage's gravity and speeds faster than light. The particle model does use Lesage's theory of gravity and states that the G2 particle moves faster, much, much faster than the speed of light. So if I would follow mainstream, I couldn't do this, but that's exactly what happens in the particle model. And it turns out that the particle model, instead of having 4 main forces, has two forces. Gravity 1 causes atoms and molecules and larger objects to move in an organized way, as in Newtonian gravity. It moves the apple towards the center of the Earth, and it causes the moon to orbit the Earth. And generally, gravity 1 is in the first realm that Smolin talks about. Gravity 2 causes the N1 particles to bind together. N1 is the name for the nucleon, and hence it's the nuclear strong force. Gravity 2 is the nuclear strong force. Gravity 2 causes particles to orbit the nucleus. So it's the atomic force, binding force. G2 causes the G1 particles to move in an organized way in the form of magnetic fields. That's the electromagnetic force. All of this is in the second realm. Excuse me. Coincidentally, there is no nuclear weak force in the particle model. Maybe I need to go to a discussion about black body radiation. I've mentioned this before. I still haven't done it. But specifically, I have not found in the particle model any force that relates to the nuclear weak. The electric force, which they ignore, is G2 gravity, or G2 gravity replaces the electric force. When the particle model is applied to certain applications that require a force that is not one of the four forces, it often shows up in the same place, excuse me, as the electric force. For example, in an electron gun, voltage is applied to the gun and an electric field is developed, and they show that field by putting vectors from the anode, pointing from the anode to the cathode. That's the electric field that they show is there. The particle model states that there's a G2 particle field around the electron gun. There's a whole field of particles coming at the electron gun, and a net G2 field is generated from the anode to the cathode because of the G1 particle distribution that's being developed by the voltage. Voltage is pushing the G1 particles through and around the gun. Thus, G2 gravity replaces the electric field, and I also found this to be true in diodes and transistors. Here's the irony. The one force that is missing in the standard model, the electric force, is actually the primary force behind all the other forces in the microscopic realm. So the irony is, to me, is they discard the one they need. So back to problem 1, quantum gravity. General relativity and quantum gravity are separated because they are caused by two different gravities. Each gravity force is in its own level. In one sense, mainstream science got it right. There are two realms, and the realms, as the particle model, as I understand it with the particle model, is the realm of level 1 and level 2, gravity 1 and gravity 2. So Lee Smolin says, okay, find a single theory that combines general relativity and the quantum theory into a single theory that can claim to be the complete theory of nature. And quantum mechanics claims there are two realms. Well, I don't know whether you can call it a single theory or not, but we certainly have a unifying concept with the concept of gravity at the two levels, where these gravities are mechanical in nature, not electrical, not electrostatic, not magnetic. These are all mechanical. And the two realms of this unifying concept are level 1 and level 2. This is just a repeat of what I've already said. Gravity 1 is the Newtonian force of gravity. Level 2 is gravity 2. And gravity too is the nuclear force and is the electric force, both of them. One force does two things in that sense. But the magnetic field is not uh, G2 gravity. That's not what it is. G2 controls the magnetic field, and the magnetic field is made up of G1 particles orbiting around and through the magnet. Two realms, but they're level 1, level 2, gravity 1, gravity 2. So they're unified in the concept of gravity. Conclusion: forcing general relativity fit quantum theory is the wrong approach. Scientists knew in 1785 that Coulomb's law worked like gravity. They saw it. Even so, they ignored one of the best clues. So they spend many man-hours and lots of money pursuing string theory. By the way, string theory is a theory of quantum gravity, and there's no end to sight in their working on such theories. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll talk more about the universe using the particle model. Thank you for your attention.